I'm Mohammad Rayyan Khan. Today I'll be talking about how we can balance energy yield and economics in terms of cleaning solar farms. The story of the PV industry or the system starts with a cell. You would design the cell to get maximum possible efficiency. You would look into the electrical properties, the optical properties. Then you would form the module or the panel. There you think about how to do the fin and the bus bar layouts. And then you do the packaging, and then these get transferred to a farm, and you get a big array of PV system. Now, for a large farm, you can think about the system in several different ways. Of course, you have the utility scale or conventional farm. There are also building integrated PV systems. You can have floating PV. You can have agrophotovoltaics as well. So in each case, the orientation, the spacing, the ambient conditions are going to be different. That is why the lifelong assessment should be understood very well so that you can map all the systems into this analysis. For lifelong assessment, you can think about it in terms of output degradation, which is non-permanent. You can clean the panels, but the module degradation, that is permanent. So you'll have a degraded panel every year, and at the end of its lifetime, after 20, 25 years or 30 years, you'll have to recycle it or replace it. Now, all of this is driven by minimizing LCOE or minimizing the cost of operation. Now, today we'll be focusing mainly on soiling. So let's see how things look. In terms of insolation, within the sun belt, the insolation or the sunlight is the highest. But the bad news is that in many locations within the sun belt, the dust or the soiling rate is high as well. So the question is, are we going to lose a lot of money because of soiling? So that's what we are going to discuss about in this talk. So soiling on solar panels can be the concept or the discussion can be subdivided into two parts. The first is a general soiling analysis and a global picture. And then once you understand the general physics, you can go into end-to-end modeling for specific locations and designs. So let's start with the general analysis. So what happens when a module catches dust? Well, you see a blurry image of the sky and the sun. So you get less sunlight into the cells, and lower amount of sunlight translates into lower output. Now, let's say you take the ratio of unclean to clean panel output. That is the performance factor or the performance ratio. If you leave the unclean panel as is, it's going to catch more and more dust every day, and the performance factor is going to degrade. After a certain time, you can have a cleaning intervention, and the output is going to immediately recover, and then it will start falling again because of dust accumulation. If you have periodic cleaning, then this process keeps repeating itself. Now, this is only true if you have constant or similar rate of soiling. You can have sandstorms at certain locations, In those cases, on a day when you have sandstorm, the output is suddenly going to drop because of the excess sand deposited on the panels. And you are not going to recover the output until the next cleaning intervention. Now, things are better when you have rain, right? On a rainy day, the output is going to recover, or the panel is going to clean itself. But the thing is, you don't really want to clean as quickly this time because you have a cleaner panel. So now that we understand the basic scenario of soiling, let's look into the energy output or the energy lost. The shaded region shown here actually integrates and gives you the net energy or revenue lost. If you clean the panels even more frequently, the energy lost would be lower. Now, the area under the curve represents the energy output, right? You can multiply the performance factor with a clean farm output, and that gives you the daily energy output. Once you sum it over the whole year, you get the energy of these panels over the whole year. Now, whatever energy you get, you can sell, and that's your revenue. If you clean the panels more frequently, then you lose money. And the total of these two gives you the net revenue. The goal would be to make a balance of these three things in order to maximize revenue. So let's talk about a specific case. For example, in Ruma in Saudi Arabia, this is the insolation, and you also have the soiling rate of the whole year. So the known information are insolation, soiling rate, you of course know the tariff rate, and the cleaning cost of the farm. The goal is to maximize the revenue, or in our case, we maximize the normalized revenue. So if you vary the cleaning cycle and see how the revenue changes, if you clean the panel every day, well, you would get more output, but you lose money because you clean the panel every day. If you wait too long, then the output is lower, although you don't use up too much money to clean the panel. But there is a maxima in between where the revenue can be maximized. For example, here it's about 6 to 7 days. And if you can optimally clean the panels, you minimize your loss to 1.6%. Of course, if you have rain, things are better. Your losses don't accumulate as fast. And if you have sandstorms, things are really bad. If you wait too long, the output is going to degrade very, very quickly. Even if you optimize your cycle, it's worse than not having sandstorms. But how much revenue would we actually lose? So companies would usually assume 3% profit loss due to soiling. That's more or less true if your output loss per day is low. But depending on your location, it can be higher. And depending on how long you wait, your revenue loss might be even higher. So if your cleaning interval is wrong, you might end up, let's say, with a 10% loss. A 10% loss means you would lose 2000 US dollars per day for a 100 megawatt peak solar plant system. Now these things would change if the profit losses are lower, or the tariff rates or the cleaning costs are different. Now let's have a look at the global picture. Of course, we can gather the information for daily GHI. We have made an estimate of a global picture of soiling rate using soiling experiments from literature from about 130 sites over the globe. You can see that there are patches here which show that soiling rate can be very, very high at certain locations. It's medium around here, and then for other parts of the world it's pretty low. Now based on these two information, we can use this simple formula to find out what is the optimum cleaning cycle. So it depends on the cleaning cost, soiling rate, tariff rate, and the output, which depends on the GHI. So here's the optimum cleaning cycle. The dark parts are the bad ones, or the bad situations where you have to clean the panels maybe 5 to 6 days. There are locations where you can wait a month before you can clean. Finally, you can use this equation to find the normalized revenue based on all these information. And here's the normalized revenue. Again, if you look at these parts where the soiling rates were higher, you can see that the optimum revenue is even lower than 94%, which means you would lose more than 6% of your revenue even if you clean the panels optimally. You cannot have anything better than this. Now, for all these calculations, we assumed a fixed tariff rate and a fixed cleaning cost, but that is not actually the case. In Asia, soiling is higher, but the cleaning costs are usually lower. If you go to Europe, the soiling rate is low, but the cleaning cost is very, very high. What happens in the end is that once you balance everything out, you have 2 to 5% loss revenue anywhere over the globe, even after optimal cleaning. Now, coming back to the question, are we losing a lot of money because of soiling? Well, yes, we are losing some money, and we want to maximize our profit. But this might look bad in terms of sustainability if we are not cleaning the panels optimally. You can see here Asia has the highest soiling rate, and after that we have Middle East and North Africa. If you look at the PV capacity, Asia leads by a lot compared to the other regions, and by 2030 this capacity is going to increase by 5-fold, which means you are going to keep on losing more and more money if you do not clean the panels optimally. Now let's go into further details. Instead of doing a generalized picture, can we do end-to-end modeling and prediction for a given location? So what do we know about PV output and soiling? Well, we can accurately model PV farms. It could be a monofacial farm, it could be bifacial, it could be vertical, it could be any tilt angle, any location over the globe. And we can do soiling experiments. We can find out the soiling rates, right? Feed it to our soiling model, and using that soiling model, we can do cleaning cycle analysis to find the optimum cleaning cycle. Now, this doesn't really tell you which of these farms would be best. That is why we need to couple the PV model with the soiling model. We need to figure out what is the yield under soiling and then figure out what is the revenue. So let's start from the beginning. We would do soiling experiments. Let's say, for example, here we have 2 panels tilted at 24 degrees facing the south. One is clean, the other is unclean, and if you take the ratio and take the reading, you can figure out how much loss you get from these panels. Now, the soiling rate that we got from our location is about 0.78% per day, which is pretty high. Now, if we consider a panel at 0 degrees, which is horizontal, we would of course expect much higher soiling rate, and that is the case. We do see a soiling rate which is double the previous value. And if you look at panels at 90 degrees, the soiling rate would be pretty low, as you can see here. Now that we have the soiling rates for different tilt angles, we can figure out what would be the soiling loss factor depending on a certain cleaning interval. For example, let's say we choose a cleaning interval of 40 days. So the output would be decaying depending on the soiling loss we already figured out. Then after cleaning intervention, it will periodically have that same profile. For 24 degrees, it's slightly better because the soiling rate is lower, and things are much better for 90 degrees. And this is just the soiling factor or the performance factor. Now let's have a look at the output from the PV model. For that same timeline, we can figure out what is the insolation, right? So you can download it from any database like the NASA database or the NSRDB database, and using that you can figure out what are the output of the 3 different configurations. For example, here we have 2 monofacial configurations. One is at 0 degrees, another is at 24 degrees, and we have a bifacial vertical panel array with extra reflection from the ground. Now you can figure out the output or calculate the output in an hourly basis and then integrate over time to get the output for each day. So this is the array yield without soiling. This is the clean panel output or the clean array output. And we have already figured out what is the fractional soiling loss in each of these configurations. Once you combine these outputs, you get the array yield with soiling. So remember this formula we already discussed. You multiply the soiling factor with the clean farm output and then integrate or sum over all the days. So now that we have yield and soiling, let's have a look how they compare. Of course, the 0 degree panels, they have the lowest output. They also have the highest soiling rate, so things are looking pretty bad. For the 24 degree south panels, usually these will give you the highest yield. However, this will degrade if you wait too long to clean the panels. For the vertical bifacial panels, these would give you higher output if you have a cleaning cycle higher than 20 days. Now remember that we should not be trying to optimize the yield. We really need to look at what is the revenue. So once we do the cleaning cycle analysis for revenue, this is what we get. So if you can clean the panels before 25 days, of course, the 24 degrees south monofacial panel is the best. And in that case, the optimum cleaning cycle is 6 days. If you need to wait more than 25 days to clean the panel for accessibility issues, then it seems like you get more revenue if you use the vertical bifacial panels because they have lower soiling. So it really depends on your application and the accessibility on how you want to clean the panels to get the best possible revenue. So here's the summary. You start off with the soiling experiment. You have the soiling model from the soiling rates. You have a PV model to get the clean panel output, and you merge with the soiling model to get yield under soiling. And then you do the cleaning cycle analysis to compare the revenue and figure out what is the best possible scenario or the best possible configuration for your location. So at the end, the general soiling analysis gives you the generalized picture, and you can have a global picture of the soiling scenario. However, for a specific location, you should look into the end-to-end modeling and prediction process. Now, looking ahead, we actually need more soiling experiments to do a global analysis. This is why. You see the red dots here? Those are the locations we used to have or get an interpolated world map of soiling rate. There are a lot of blank spaces, and we really do not know if the interpolations are correct at those locations. Then there is this issue of sudden events, for example, rain and sandstorms. If you take these into account, then the question is, would seasonal cleaning cycles be better? Of course, another issue is partial shading if you have non-uniform soiling. Although I am showing a picture of snow, well, it is also soiling on the panels, not with dust, but with snow. So this is another thing we need to look into. How much energy would you lose if there is partial shading? And finally, we need a proper estimation of soiling at a given location for all the configurations to properly address the end-to-end prediction. But you need to remember that all these analyses would be possible only if you know soiling rates and, say, rain and sandstorm statistics beforehand. The thing is, you'll not know this beforehand. For any location, the soiling rate this year might be wildly different from something what is going to come after 5 years. Also, another good example is rooftop PV, for example, on big industries. Those will not be correlated to weather, rather it depends on the traffic close by or the fumes exiting from the industry. So we really do not know the soiling rates beforehand. So we need a real-time cleaning algorithm at the end. Now, to reach this endpoint, we need to understand all the physics behind it, and hopefully will finally have a real-time cleaning algorithm. To me, that is the end goal of the soiling prediction for in-field analysis. I would like to thank my students and RAs who have been working hard for all the experiments and the analysis, and our collaborators at East-West University, Purdue University, PVQAT, and United International University. I would also like to thank the funding bodies, the engineering department at our university, and UIU-IAR and BDREN for supporting us with computational facilities. Hopefully, you have been able to get a good picture of how we should balance yield and economics for soiling and cleaning of solar panels. Thank you so much.